All right, so we're going to start section 6.2. I'm going to go ahead and warn you, this one is a little more difficult than the stuff we've seen already. So we're going to use these one-dimensional integrals to deal with volume. And it's doable. We're going to talk about how to do it. We're going to see some problems. There are easier ways of calculating volumes, and you'll learn them next semester if you move on to Calc 3. But we're going to focus here on just using what we know now. So I want to kind of point something out because I don't think this is um, people realize this enough. But if I want to calculate the volume of a cylinder, so what you'll notice is if I have a cylinder, I need to know the radius and I need to know the height, and the volume of this thing ends up being pi r squared h. Then you go through high school and, up until now, you think, okay, that's a formula I have to memorize. I don't have this formula memorized. I just know how to calculate volumes in an intelligent way. I'm going to show you how to do that now. So what you can do when you're trying to calculate a volume is you can look at, the cross section of a volume, and the cross section is just a two-dimensional, cutout of segment of the volume. And then, if I want to figure out the volume of this thing, the volume is going to be, so for this thing that doesn't, where the cross-sectional area doesn't change, it's going to be so you'll see that the cross-section here is a circle, right? So what I can imagine then that this is then pi r squared, which is the area of a circle, multiplied by the length of the cross-section. And this works for any kind of volume, as long as your cross section is not changing. If your cross section changes, this is when you need to start pulling out calculus and using those tools. So, the volume of a box of a rectangular prism, length times width times height. That's the same idea. Your cross section there is a square. So length times width, or is a rectangle, so it's length times width, and then you multiply through by the cross section, length of the cross section. So we're going to use this idea to generalize to volumes of other shapes. And this is where you're going to, I've said it before, but you're really going to see it now. I am not an artist. I'm going to try and draw these things. You can look in the book if you need to see what I'm trying to draw. It is bad, but so, already messed up. So I'm going to try and draw this first thing in the book. So they draw something that looks like this, something that looks like this on this end. And then it's connected. So the idea is, with this, if I wanted to calculate the volume, what I can do is I can look at a little cross section of this. And let's assume that the cross section has width dx. So it's just a really small segment of this thing. So what I can do is I can figure out, if I can figure out what the area of this cross section is, then, on this really small length, the area that I'm using doesn't change. So then, oops, sorry. So because the area doesn't change, I can, assume that it's constant. Then I have the infinitesimal volume. dV is the area of this thing times it's the length of the cross section, dx. Now, if I integrate both sides, I'll get the volume is equal to the integral a dx. So what I'm doing here is I'm assuming that the area is a function of, where I am on this x-axis, because you can see that this thing has cross sections of circles here, but the radius of the circle changes as you go along the x-axis. So if I want to figure out a volume, I just integrate the area and then multiply that by dx. So let's do an example then. All right, so let's do an example. We're going to show the volume of a sphere is 4/3 pi r cubed. Okay, so what I'm going to do is I'm going to try and draw a sphere, and it's not going to be very good looking. So if I have, this, that's better than the first one I drew. Okay, so the idea behind this one is, I'm going to integrate along the x-axis. So I need to do cross sections that, let me use a different color. So I need to do cross sections that look like this. So I need to integrate, imagine dragging this cross section, across the sphere, dragging it here, maybe even here, as I'm adding up all these areas or all these volumes. So the idea is I need to figure out what the area of this circle is. And the way we can do that, so the way we're going to do that is we're going to think about it like this. So this sphere has a radius r. Let me draw it, sorry, changing colors. So the radius of the sphere is r. So one thing I can do is I can look at, I'm going to go ahead and delete that. Oh. So one thing I can do is I can look at, I know that this length here is r. This length down here is x, and then on the circle here, we have a second radius that we're going to call y. And so what I know then, and r, remember here, r is a constant. It is, it's always fixed. What I can look here then, what I can see here then, is that my area then is going to be pi times y squared. So the cross-sectional area is the pi times the radius of the circle that I've drawn squared. Well, the radius of the circle is y, so it's pi y squared. But I'm not integrating along y, I'm not integrating up and down. I'm integrating left and right, so I can't leave it in terms of y. So I'm going to use the trigonometry of this triangle to figure out what y is in terms of x. So I already know that x squared plus y squared is equal to r squared because of it's a right triangle. So from this, I can figure out y squared is equal to x squared minus r squared. Sorry, r squared minus x squared. So then my area, my cross-sectional area then is pi times r squared minus x squared. Now, if I want to figure out the volume, I'm just going to take the area, multiply it by, multiply by an infinitesimal with dx, and I'm going to integrate that. And now I need to go from, this point of this x value of the sphere to this x value of the sphere, but I know what those are, right? So this sphere has a constant radius, so this distance here is r, and this distance on this coordinate here is r, and on the left-hand side, that coordinate is minus r. So this integral is going to go from minus r to r dx. Now I'm just going to plug in. So I'm going to get the integral minus r to r. The area is pi r squared minus x squared dx. And now I'm going to integrate this. So first thing you should notice is that this is an even function. So it's x squared and x to the 0. This is even. If I plug in minus x, I get the same thing back. So I'm going to exploit that and make this 2 times the integral from 0 to r, pi r squared minus x squared dx. And now I'm going to do this integral because it's a little easier to do. So this is 2 times, so I'm going to do 2 pi times the integral of r squared is r squared times x. The integral of x squared is x cubed over 3. We're going to evaluate this from 0 to r. So this is then 2 pi times r cubed minus r cubed over 3. And if I subtract off, plugging in 0 here, I just get 0. So I'm left with that. So this is 2 pi times r cubed minus r cubed over 3 is 2r cubed over 3. This ends up being, when you simplify, 4/3 pi r cubed. So we proved that, the volume of a sphere is 4/3 pi r cubed. So just I kind of want to go back because I know this stuff is really confusing. So the first thing I did is I wanted to come up with an expression for the area. So I drew a cross section in blue here, and I noted, okay, it's a circle. I know the area of a circle is pi r squared, but in this case, my radius is not the radius of the sphere that I've drawn. The radius of that circle is, the y value there. So when I label all these things x, y, and r, so this thing here, this area, I don't want it in terms of y because I'm integrating along the x-axis. So I use the fact that I know use the trigonometry here to come up with a relation between x and y. Using that, I can plug it into the area and get something in terms of just x. And then from there, I'm able to integrate that and get my answer there. So 4/3 pi r cubed. Again, I know this stuff is really some of the more difficult stuff. So if you are struggling with this, you are welcome to email me, come to office hours. We will do a couple examples together. It'll hopefully make a little more sense. Okay, so let's move on to the next example. So with these, you have to really just draw it out and figure out what's going on. So next example is find the volume of the solid obtained by rotating the curve y is equal to the square root of x from 0 to 1. Okay, so let's go ahead and draw what this is. So I have the square root function from 0 to 1, and what I'm doing is I'm rotating this thing around, and I'm getting a solid that looks like this. And so the idea is I want to do the same exact thing. I'm going to draw, a cross section. I'm going to draw a cross section of this thing, and I can automatically see that this thing has cross sections of circles. So what I'm going to do is I'm going to write down the area of that circle. And again, I can already tell that, if I look at this thing, if I want to figure out what the radius of the circle is, I can already tell that it is, given by the y coordinate. So this thing here, so this height here is y. So my area then is just pi y squared again. So, and just like before, sorry, I'm going to switch back to black. Just like before, I don't want it in terms of y, I want it in terms of x. But the good news is I already know what y is in terms of x. I have y is equal to the square root of x. So this is a little easier in the sense that I can just plug in. Area is equal to pi times y squared. Y is the square root of x. I'm going to get the square root of x squared. This is just pi times x. So now if I want the volume, that's going to be the integral a dx. This is the integral pi x dx. We're going to go from 0 to 1 on here. Sorry, I forgot to fill those in. And now I'm just going to go through and do it. I'm going to get pi times x squared over 2, evaluated from 0 to 1. And then this is pi over 2. And when I evaluated 0, it's 0. And that is my final answer there. So this one is a little easier. We're going to get into some shapes that, aren't going to be as easy. So we'll talk about, other shapes to approximate volumes, but it's always the same thing. I find cut into cross sections. I try and come up with an area function for the cross section, and then I integrate that because the integral of area is volume. All right, so I'm going to stop there and pick up with some more examples.